Rate law shows us the mathematical relationship of a reaction rate and a concentration of either reactant and products. In this lecture, we will talk about how to derive a rate law for a multi-step reaction, how to find a rate law from the reaction mechanism. We start from a special case that the rate determining step is known. The rate determining step is the slowest step, and assuming the rate of the overall reaction is approximately equal to the rate of the slow steps. Then we try to derive the rate law for the overall reaction. Here are the examples for reaction A. There are two steps. First step is slow, is the rate determining step, and we can take the rate of the step 1 as the rate for overall reaction A. Then we write down the rate A equals rate 1 equals K1 times the concentration of A. For reaction B, step 2 is clearly the rate determining step. The rate of step 2 is equal to the rate of overall reaction. Then we have rate B equals the rate of step 2 equals K2 times the concentration of I. In reaction B, I is an intermediate produced by A, consumed rapidly to form product B. We usually do not use the concentration of the intermediate in the rate law. We should replace it. Now, we check the reaction in step 1. We can write the rate law as rate equals K1 times A. This is the rate law for forward reaction. We can also write the rate law for the reverse reaction, K minus 1 times concentration of I. Because the step 1 reaction is fast, the intermediate will not consumed by the step 2 reaction at a very small time interval. The rate of forward reaction equals the rate of reverse reaction. That is expressed as K1 times A equals K minus 1 times I. Then we have the concentration of I is K1 over K minus 1 times A. Finally, we replace 1 with this formula and derive rate law for the overall reaction. It's K2 times K1 divided by K minus 1 times the concentration of A. When the rate determining step is unknown for the two-step reaction, as an example, we first write down the rate of consuming I in step 2. Rate equals K2 times I. And we also need to write down the rate of consuming I in the step 1 as rate equals K minus 1 times I. The total rate of consuming I is the sum of the rates in step 1 and 2, as shown at the bottom of the slide. Next, we write down the rate of producing I in step 1 as rate equals K1 times A. Here, we use an approximation to assume that the rate of producing an intermediate equals the rate of consuming an intermediate at a steady state. Using this approximation, we have K2 times I plus K minus 1 times 1 equals K1 times A. Then we have the expression for intermediate as shown here. Now, we can derive the reaction rate in terms of producing B. Rate producing B is K2 times I, which is rewritten by replacing I as K2 times K1 times A divided by the sum of K minus 1 and K2. In an analogous way, you can derive the rate in terms of consuming A, which is shown on the slide. You may try to derive it by yourself. Question. Find the rate law for the following reaction occurred in 2 steps. We need to find the expression for I. The consumption of I includes a reaction in step 2 and the reverse reaction in step 1. Then we have the rate of consuming I equals K2 times AI plus K minus 1 times IB. The rate of producing I is K1 times concentration of A. Using steady state approximation, the 2 rates are equal. We have the concentration I equals to K1 times A divided by K2 times A plus K minus 1 times B. Then the rate of producing C equals K2 times I and A, where concentration of I is replaced with the above equation. We finally have the formula for the reaction rate.